This event is part of the University Sustainability Initiative. And today we are very pleased to be joined by Professor Mujtaba Abdi-Jalebi, who is a professor in energy materials at UCL. His research focuses on the properties of emerging nanomaterials and semiconductors, and that is to integrate them into technology like solar photovoltaics, in order to advance a net zero future. And beyond his research activities, he's actively engaged in bridging the gap between industry and research, and is trying to commercialize new technologies like photovoltaics, carbon capture, and green hydrogen. And today he'll be talking about some of his research. So if you have any questions, you can type them up in the Q&A in the chat. And so the last 15 minutes, or even earlier, if the talk finishes earlier, you'll have time for questions. And now I'll pass on to Professor Abdi-Jalebi.
Thank you so much, Ishal, for the kind introduction. And yeah, I'll start in a few minutes. So in between, could you tell me a little bit about the audience? That we have audience from UCL, or we have also audience from outside UCL?
So
which kind of backgrounds?
So like we have audience from different universities. So it includes like UCL, Cambridge, Oxford, and LSE, and Imperial as well. And yeah, at least for our Energy Society at UCL, it like I would say around 40 to 50% of the students are the ones who are doing masters in energy and data analytics at UCL. But then we also have like in our society, we have people from various backgrounds, like it can be just chemistry, physics, even like more to do with like the policy side as well. So yeah.
That's very interesting. No, that's a very broad and nice background. Thanks for the brief explanation. All right, so I'll start now. Thanks very much, UCL Energy Society, for the kind invitation, and welcome to everyone who's coming from either UCL or other universities in the UK. So I hope this presentation will be useful for everyone. So today I'm going to talk about next generation solar energy materials and devices. So briefly, before that, I introduce myself very briefly. I know Ishal already done a brief introduction, but I'm Mujtaba Abdi-Jalebi. I'm Associate Professor at UCL Institute for Material Discovery, and I'm the head of Functional Materials and Energy Devices Research Group at UCL. And I'll give a brief introduction about our institute, my group, what sort of programs we are teaching and doing research on. And then I'll start with a brief overview of the role of solar power in the energy transition, both in the UK and also beyond, globally. And also potential integration of solar with other technologies, some example from my own research group that we are working on developing materials for solar energy and solar fuels. And at the end, I'll finish my presentation with giving you some challenges and opportunities that are rising in the future. All right, so a brief about myself. So this is my academic journey. That comes to UCL. So I did my bachelor in material science and engineering, and master and PhD, master also in material science and engineering, and PhD in physics. In master, I have done it in EPFL in Switzerland, and I did my PhD in Cambridge University. Did a fellowship afterwards in Cambridge as well, and then I joined UCL since 2019. And I've been working on materials for energy application in the almost past, when I started my bachelor, over 10 years now. And sort of since then, I've expanded my sort of knowledge on various aspects of the materials and also the engineering aspect, as well as the sort of the chemistry, the physics of the material, and how to make them work better in the device, and they can also last longer. All right, so I am based at the UCL Institute for Material Discovery. So in this institute, we work on many different topics, all related to material science, but in different discipline in terms of like energy generation, energy storage, biosensing and biomaterials, automated materials discovery, and also data-driven material science. These are some pictures that shows the various sort of research we are doing. We are based in the Bloomsbury campus at UCL. And in our institute, we offer 5 master programs ranging from energy storage, sustainability, materials innovation and enterprise, data-driven material science, and also on advanced material science. And just because some of you might be from undergraduate, so I thought maybe it's useful to give you an overview of what we teach. So if you're interested, please do get in touch. We can provide you more details. So this is the structure of our MSc programs. All right, so about research. So in my group called Functional Materials and Energy Device Group, or FMED or FMET, so material discovery, synthesis, and characterization is the core part of the group. So we started from materials and doing all kind of optoelectronic and structural and morphological characterization, and doing a lot of different types of deposition of the material, and put them in terms of devices and application. There are 2 major applications that's in my group we are following, or we are sort of developing. One is optoelectronic devices. So when we say optoelectronics, so that means a combination of optics and electrics. So that means like solar cell devices or LEDs or X-ray detectors or photo detectors. So these are some examples. And the other aspect is about green fuels. So when we call green fuels, so that means the fuels that are sort of prepared from green sources like solar or wind or any other renewables, which I'm going to talk about them towards the end. Right, so a little bit more like scientifically. So basically, this is the material so-called perovskite, which I'm going to give you some example in the upcoming slides, that have been like the core, so one of the core focus of my research in the past decade, to develop this material and make it suitable for various application by playing with its chemistry, like optimizing its composition, or by sort of changing the dimension of it. So you can make them 0D or sort of 2D or 3D, depending on how you sensitize them. Let me see if I can activate my laser pointer. Yes. And the other aspect is about utilizing solar energy and utilizing it in a way to produce green fuels, such as green hydrogen. So how this works is we can utilize this device, so-called photoelectrochemical cell, that can sort of get the energy from the sun and then split the water into oxygen and hydrogen, and you can extract the hydrogen and sort of pressurize it and use it as a fuel. Or you can have another route to have a photovoltaic cell that combined with an electrocatalytic device that can sort of utilize solar energy again and electrolysis and produce hydrogen. So this is another sort of a schematic that shows the process. So basically we split the water into oxygen and hydrogen in anodes and cathode, and this system is powered by solar cell or by photovoltaic cell. And another aspects in my group, we are focusing on to have a circular carbon economy. That means when we develop this cell, so basically we get all the CO. This is another aspect about CO2 conversion. So basically we capture the CO2 from either directly from the air or from from energy intensive industries, and then convert it to some useful chemical such as methanol, which we call it green fuels as well. And then methanol could be used in many different applications, like in transport and fuel cell, and then get back to the homes. And then this complete the whole circular sort of cycle. So I'll talk about it a little bit in more details in the coming slides. All right, so that was a brief introduction about myself, about my research group, my institute. So again, if any of these topics are of interest to you, or you want to do a master study with us, please do feel free to discuss with me, or feel free to drop me an email. You can find my email address in the bottom of almost each slide. So just to remember that you can contact me. All right. So why we do this research? So, or why you guys come to this probably session? One of the aspects is about the climate change battle that we are all sort of facing at the moment. And one of the aspects is about this temperature. Maybe some of you already heard about. So it's 1.5 degree threshold. So this is all about this plot. So basically, this plot is showing the temperature of the world over time, starting from the pre-industrial revolutions in 1850, and then how much it increased since then and now, and what is the projections. So what happened is you can see after the industrial revolution, there has been a almost exponential growth in the increase in the temperature, which is very catastrophic. And we are currently in this stage, as you can see, which is very close to 1.5 degree threshold. So the question is, if we pass these thresholds, there will be a lot of events or catastrophic sort of consequences that are irreversible. So it's very important that we stop this trend, and we sort of by implementing some policies, some work together with governments. So it's a sort of a multilateral sort of efforts by government scientists, policymakers, also the people who are sort of living in this planet, to avoid this to happen. So so this is also the reason that the Paris Agreement also come to place as well. So this is one of the major sort of topics that was discussed, and came to an agreement that every country in the world to limit their emissions by 2050 to become zero. So zero emission or net zero. You might have heard these keywords in the news or in different resources. So this is all about this temperature rise. And obviously, I summarize what will happen here for you in this slide if we don't stop this increase in temperature of the world. So that will be extreme weather events or sea level rise or impacting our ecosystem and biodiversity. And we also actually feel that these days, right? So if we look at, I got it from the BBC Weather and BBC News, about the heat wave we noticed this summer, and in some countries around Europe as well. And there have been a lot of studies that shows these heat waves and this sort of change in temperature is directly related to human sort of activities and the temperature rise I mentioned earlier. So this means that this is actually very, very sort of critical at the moment, and it's come to our life more and more when over time. So let's talk about. So I'll talk about the problem so far about the temperature rise in the globe and what will happen. So now from here onwards, we want to discuss about the solutions, how we can combat this challenge, which is a global challenge on climate and sort of decarbonization. So one of the solution is which have been quite sort of obvious in the past decades was turning all our energy resources to renewables. So when we call renewables, so these are the major ones that are listed in this slide. So ranging from solar to wind to biomass to hydropower, geothermal, etc. But if you look at the capacity, you can see solar is by far the largest available energy source that we have. So it's and compared to other like wind or hydro or geothermal. So this is showing the capacity of the solar energy compared to all other renewables altogether. In also comparison with other finite resources like natural gas, petroleum, or uranium or coal. However, on the other side, the current utilization of this is quite limited. So it's only a very tiny percentage of this abundant resource that we have. So to give you a context, this big cube, this red cube is showing the instantaneous rate of energy from the sun hitting the earth, which is about 200,000 terawatts. And if you compare it with total global power demand, it's about 20 terawatt at the moment, and it will projected to be increased by to 30 terawatt by 2050. So you can see that this is still a negligible or very small portion of the most abundant sort of resource that we have. And if you look at the current photovoltaic installation, so photovoltaic, which I'm going to explain to you in a moment, is a way to capture the sunlight and turn it into electricity, which is the major sort of source of solar energy utilization. Is quite limited. So you might not even notice that there's a very small red cube over there. So it's almost a little bit more than 2 terawatt now, the percentage that we are using at the moment. So now if you look at the global energy consumption by sources, this is actually very recent. I just got it from this website today, from Our World in Data. You can look at this. This is a very interesting website I will suggest for you to look at. So it shows that the changes in energy consumption since 1800 until actually now in 2025. So normally the data are a few months back based on what they got, but the analysis have been done based on 2025. All right, so what is important here is you can see that obviously global energy demand increased. That's an obvious conclusion from this. And the other thing is you can see there are some new resources or new renewable resources that come to the play as well. So like nuclear or solar, wind, and other renewables such as biomass, etc. But still there are huge energy consumption are coming from natural gas, oil, and coal around the world, which is not ideal because all of these oil, gas are the source of CO2 emission, right? So which is we want to limit to combat the climate change and that 1.5 increase in the temperature. So if you look at the share of primary energy consumption in the whole world, so this is the map of the world, you can see that so this is from the renewable sources. So which countries are more active in renewables? So you can see Brazil, it's producing 50% of their energy from renewables, which is very promising. You might not expect that. And Chile is about 32%, UK 21%, Spain is 26%. Norway is the leading country in this, so it's over 70%, which is quite significant. We should learn from Norway actually. US 12 and China 18, Australia 15. So you can see that the major countries are trying to adapt, but their speed are not that significant. A smaller country like Norway are being very successful, but in the larger scale, like in China or even in India, you can see that the percentage is still not that significant. And now if we limit that renewable to only solar, so solar energy, you can see that some countries are leading compared to others, but still you can see in almost all the countries, the maximum percentage they got for their energy consumption is less than 10%, which is a value we need to think about and why we are not increasing that more significantly. So in the US is 2.8%, UK is about 2%, in China is about 4%, Australia 7.5%, Chile is leading here 9.9%, and in Europe, Spain is leading 8.6% of their energy is coming from solar. So obviously it also depends on the geographical location. Some of these countries obviously have more sunlight compared to others. So it does make sense that some countries have a higher percentage, like Brazil or Chile or Australia. But I mean, we would expect if you want to reach net zero, this percentage need to increase quite significantly. All right, so if you just look at again another chart for you to look at. So again, oil, coal, and gas are keep increasing in the past decades, which is not ideal. Good news is some renewables are becoming more and more popular and coming to the market, like solar, wind, nuclear, hydropower, but it's still not even a third of the coal and gas and oil, right? So we are still far from the full exploitation of the renewables. If you just look at the UK, good news is UK has limits the utilization of coal quite significantly. Nowadays is less than 1%, which is a good news for UK. But it's still oil and gas are the major energy sort of consumption by oil and gas. And solar and winds are growing slowly to some sort of good percentage. And wind has been very active in terms of all other renewables. Wind was the most popular one in the UK, obviously because of, again, geographical location. So this is a little bit more details comparing UK with other countries around the world: US, Japan, Germany, South Africa, Brazil, India. And you can see that the amount of energy provided in different sort of sources: wind, solar, hydropower. And just if you look at the UK one again, so we can see that bio energy is 50%, 50%. This is just for the renewable, yeah? So not for the whole UK. Of course, for the whole UK, oil and gas are still the majority. But if you look at the renewables, the major renewable in the UK is coming from bioenergy, from waste, from wind and marine, 25%. Solar is a still lower percentage, like about 4%. So another one about the UK one. So this is again only for renewable sources since 2000 and until now. These are actual data. Yeah, these are not prediction. This is actual data. So you can see that the hydro have been quite constant over the past decade, 2 decades, and bioenergy increased quite significantly. Offshore wind and onshore wind both are playing a huge role in the renewable sort of energies mix of the UK. And solar is keep increasing and mostly started from 2012, but is still a not significant portion. But on the other hand, if you look at the smallest scale renewable capacity in the UK since 2010 until now, you can see PV was leading. So when we call it smaller scale, that means a decentralized power generation, right? So not all, not like like a farm or a wind farm or solar farm. It's mostly like a utility scale in commercial buildings, etc. So in that scenario, PV is leading even better than wind and hydro. And the final one is about renewable energy in the UK by type of the fuel. And you can see that the wind and solar is keep growing since 2000, and that's good news. And the gas is still playing a huge role. And this is a little bit more details in terms of percentage. So in 2023 to 24, we have increased the wind and solar by about 2%, which is quite promising. And nuclear was almost a constant, about 13 to 14%. All right, so now a little bit on the deployment of the PV and what are the key challenges. So the major two challenges are cost and performance, cost and efficiency, we call them. So the projections are very positive. So basically, it's showing that the cost is even going further down over the next couple of decades, which is very promising. So it's make the full exploitation of PV technology even easier for many countries. And the other one is efficiency. So another limiting factor for solar cell technology, that its efficiency are limited based on thermodynamic sort of limits, which we are going to talk about it in a moment. But it's mostly because of the amount of energy we can capture from a solar spectrum is limited based on the material that we are using in a solar cell. So this is the list of the material and how much efficiency we can get from, like, let's say, crystalline silicon, gallium arsenide, perovskite, etc., based on their bandgap. But the PV module price has reduced 100 times since 1980, which was the major application was PV for a space application, and almost 10 times since 2010. This is a huge reduction in a renewable technology, which is great news actually for solar energy utilization. And the sort of the cost reduction and the cumulative solar power are always better than what we have been predicted. It's mainly driven by this reduction in the cost. So cost reduction is mostly referred to the cost reduction in the raw materials and manufacturing. So basically, we become better in manufacturing solar cell materials and devices. And also we developed the efficiency of these devices over time. So these are all contributed to better cumulative gigawatts installation for solar power. And in some part of the world, like in UAE or in some country which has a very hot sort of weather or a very good amount of duration of solar sort of illumination, so the solar PV is actually cheaper than coal and other conventional source of energy, which is a great news actually. So that means a great progress. And both wind and renewable, offshore, onshore, and PV, the cost of utilization of these renewables are coming down significantly. So I mentioned 10 times for PV. This is a huge reduction in the cost. And now just to give you a concept, so basically if you want to go towards net zero and be more active in the area of renewables, we need to also think out of the box and talk about the full integration rather than just a conventional utilization of solar PV in solar farm or rooftop, etc. There are some new applications that can change the game. Like, for example, the floating PV. So you can basically install the photovoltaics in oceans or some we call it offshore, so floating PV. So they are on a floating sort of ground. You can also have urban PVs, so integrate the photovoltaic with the urban environments, building integrated PVs, so you can basically use this PV as a solar window or integrated within the construction of our homes, our houses, or commercial buildings. Another very good market is vehicle integrated PVs. You might have seen some of these in the market already, but not that significant yet because of the costs and some other limitations. But this is a huge market as well. And also road integrated PV, variable PVs, and agro photovoltaic PVs. So you can see that there's so many opportunities for PV or photovoltaics to be integrated in our daily life and change the game, right? So to make it more boost the percentage of energy generation from PV. So because some of you are coming from a different background, I want to just give you a brief, when I call PV, what's the meaning? So the concept or the basic definition, PV or photovoltaic, means direct conversion of light to electricity. Using some materials in this device, so you can basically generate electricity by direct light capture. This is like showing the home integration of a PV, that's how it's connected to an inverter and then to our electricity within the home or to the grid. So when you are not using at home, you're bringing the cost to the you are selling your electricity to the government and also get some money back. So this PV material or PV devices are based on a semiconductor material. Again, you might have known about what's the meaning of semiconductor. So basically, we have three types of material based on their electronic properties: insulator, semiconductor, and a conductor, which is like a metal. So what we are talking about here is about the semiconductor that's have like a energy gap between their sort of energy states, like a field band and the valence band and conduction band, that make this opportunity for this material to absorb the light and excite these electrons from the valence band to conduction bands and create the electricity. So this is a simple definition, obviously. So a common semiconductor you might recognize is silicon. It's been used in many different applications, and also gallium arsenide or germanium. So this is the very briefly showing the concept of a solar cell operation. So what happens is your solar cell is comprised of a semiconductor, which is normally sandwiched between two electrode material, cathode and anodes. So what happens is, let me see if this can go back again. So yeah, let me try it again. All right, so it absorbs the light. This plus and minus or electron holes and electrons are created within your semiconductors, and because of the potential difference within the cathode and anodes, they're drive to the opposite direction, and they will sort of collect it at the contacts, and then they will extract it in the external circuit, and then goes to the load, which is normally a lamp or battery or whatever you want, to in the form of electricity, right? So this is a very basic concept of how a solar cell works. So in terms of why, because I mentioned to you that the efficiency is one of the limitation of the solar energy utilization using PVs. And the reason is the solar spectrum that we get on Earth is looks like this. This is the spectrum of the light. This is the radiance, the intensity versus the wavelengths of the light. And you can imagine that, and this is our semiconductor that has a specific band gap, right? So if the energy that's coming to the solar cell has less energy than the band gap, obviously that cannot absorb by the solar material because this electron cannot reach the conduction band, right? So it will be just um, we call it as it's been lost, and only we can absorb the light which has a higher energy than the band gap. So then this will bring you to the conclusion that we can only absorb a very specific part of the solar spectrum based on the band gap of our semiconductor that we use in a solar cell. So that's the major limitation that limit us in terms of how much efficiency we can get. So there were two scientists, Shockley and Quasar, who studied this and find the maximum efficiency of a solar cell based on a single junction or single material, single absorber material, and that could be about uh, just above 33%. So that's the limit. So now, as a scientist, as a human, we want to go always beyond the limits, right? So we don't take the limits seriously. So we want to go beyond that. So that means we need to find some approaches. So one of the easy one is to obviously come to you already might have guessed that this might be utilize a couple of different absorber in one cell, right? So that's a very clever idea. We have used different semiconductor with different band gap that each of them can absorb a specific part of the light, and we can stack them mechanically, or we can also integrate them monolithically. So these are the two approach. And in that case, you can see that with amorphous silicon, we can absorb this part. With gallium arsenide, we can absorb this, and crystalline silicon this, and germanium this. So by combining this couple of different materials, we can boost the efficiency to very high to higher levels. And the other approach is we can also concentrate the light. So the amount of electricity we can create from a solar cell is also directly proportional to amount of the intensity of the light, right? So which is normally constant, not always constant throughout the day. But what we can do is we can concentrate the light into our solar cell and then boost the efficiency by having more intensified light. So that's another approach. So combining the intensified light plus the tandem structure using multiple semiconductor, we can boost the efficiency to over even 60 or 80%, depending on how many cells you use, how much concentration you use. So this is a sort of a way forwards to reach that. So in terms of the PV technologies, so I've summarized it in this slide. So basically, these are the major PV technology ranging from crystalline silicon to thin film, concentrator technologies, and some emerging technology, which I'm going to talk about based on perovskite or some organic material or some dye molecules. And there are obviously some novel concept that's happening as well. So, but the market leading is still crystalline silicon. And the reason is it's very efficient and it's very reliable. And it's a very mature technology. It's been there for over 30 decades. So the concept of photovoltaic is actually started initially with with this kind of material. So and most of the advancement were based on silicon based solar cells. So you can imagine why it's been so popular. And on the other hand, there are some weakness for silicon. It's thick, it's rigid, it's heavy, and it's also, and the major aspects from my perspective is that it has a very limited efficiency cap. So, but on the other hand, there have been a lot of progress since then, since the first evolution of silicon solar cell until now. And you can see that this chart is showing nicely that the module cost, which is mostly related to the cost of how we prepare the solar cell, has reduced quite significantly, which was one of the driver of the cost reduction for PV energy, the energy we got from PV. But this has become almost constant in the past couple of years. the reason that the cost of there's a cap in the production capacity of silicon solar cell is we need high temperature processing for making silicon, and this is very dependent on the also we have some issue on the supply chain as well, and this will limit the deployment of silicon PV application, right? So let's say all the politician, everyone is happy now with PV technology. If you want to go tomorrow, let's say, let's we all try PV in all countries. This won't be possible because it takes 170 years if you want to make 25 terawatts based on the current capacity and also based on the annual growth of annual growth consideration. So you can see that it's a huge timeline for making such amount of terawatt power based on silicon. So silicon is a great technology. I'm sure it will be there for many years and will play its roles in our energy mix, but it's not the only one that we should rely on. So this brings me to the new technology that can change the game. So basically, this technology is based on this simple chemical structure. It's called perovskite. It's ABX3. It's a cubic structure, and you can play with the elements of ABX. Obviously, A could be organic and inorganic, B is the metal ions, and X is the halide. But you have many sort of many kind of composition you can make based on this material using different elements. And what is important is if you look at this solar cell based on this material or based on the perovskite, it's been there first employed in a solar cell debate in 2009, and now in 2025, it's almost reached the level of silicon. So my number here is a little bit old. So now the maximum efficiency or the record efficiency is about 27%. So it's already the same level as silicon. That's great news. And the other news is this material is very cheap and is very easy to be combined with other technology, including silicon. So basically, by combining this perovskite with silicon in a tandem structure that I explained earlier, you can actually reach, again, this record is a little bit old now, but now you can reach almost 35% efficiency, which is quite significant. So I'll skip this part, but just if you're interested, you can ask question. I'll explain, happy to explain more. But the reason that this material is very interesting for solar technology or solar cells is because it has a very high absorption coefficient and it has a very long diffusion length for electron holes. And it's very tunable. So basically we can make any band gap. So we can make the full tandem structure based on just the perovskite materials with different band gaps. And this is the work we have done a couple of years ago to show the concept of photon recycling, which is another concept that's happened in the perovskite-based solar cell, where when you absorb the light, so basically this light, you can imagine not 100% absorbed by your material, right? So to some extent, some of the light or the photons gets reflected from your surface of the material or from the material. So what is important is whether the material has the capacity to reabsorb those scattered or reflected photons, which perovskite actually has that capacity. So that's enhanced the capacity of this material to even be a more sort of a popular absorber for a solar cell application. Right, so I think I need to be a little bit quicker. Almost used most of my time, and it's not halfway. But yeah, so just to give you a context that this production of silicon is very time-consuming, and also it's very sort of expensive as well and wasteful. So it's involved a lot of steps, including high temperature step. And now if you compare this chart with the perovskite one, so you can see that perovskite is relatively easy. Basically, you mix some salt, you make this solution, we call it ink, and then you can easily print it like newspaper. So you can see it's extremely simple fabrication and manufacturing of the solar cell based on this material. So in terms of all criteria, in terms of raw material costs, finished material costs, LCOE, efficiency, energy payback time, in all cases, perovskite is ticking all the boxes. So this is great news for this technology. And as I mentioned, you can make the full tandem structure just based on this perovskite material by tuning the band gap. So you can have a wide bandgap perovskite to absorb UV and visible part of the solar spectrum. And for red and near IR part of the spectrum, you can develop a narrow bandgap. And you can also combine it with silicon, as you could see these devices, and boost the efficiency significantly, over 35%. And this is the record that's been taken recently for perovskite silicon by Lungi company based in China. And also Oxford Photovoltaic is a UK-based company, a leader of one of the leader in the field of perovskite solar cell. Also reach a very high efficiency in the silicon perovskite tandem, and they also bring this technology to the market very recently, earlier this summer. And this is very great news for the field of PV. And the other aspects of PV is which new technology like perovskite brings to the play is it can offer some new application like building integrated, and also because it can be printed. So basically you can print on any substrate, including flexible substrate. So it reduced significantly the transport and installation cost, another factor to reduce the cost down. These are some examples I passed very quickly. So this is some of the installed PV modules in a real home. That was in Germany. This one is also in Germany, Fraunhofer. These are PV or solar windows. This is in Switzerland in EPFL Conference Center. These windows you could see in the picture are all a solar window. And this is a charger based on a solar cell. And this is a backpack, another product that you can sort of integrate solar cell in a consumer electronics. And also another aspects or benefits of PV that can not be produced by other renewables is a smaller scale that we talked a bit earlier, that can bring life to many people who have not access to direct electricity. Even now in 2025, there are about 700 million people who do not have access to electricity in the world, which we cannot imagine actually, right? Our life without electricity, right? Or many people are having like interrupted access. So you can see that having solar energy and utilization of solar energy using PV can bring electricity to their life, and this will increase the quality of their life quite significantly. All right, so I'll talk about the technology, and I need to be a bit quicker. Now let's discuss about the challenges. So this you might say, okay, this technology is fantastic, it's great. So why it's not been in the market already? So like other material technology, there are some challenges here as well. And these are the major three. So one is on scalability, one is on the reliability or stability of this solar cell, and the last one is on the efficiency. So on the efficiency and on scalability, have been fantastic progress in the past 5 to 10 years. And nowadays we can make a very good solar cell with high efficiency at larger scale that are almost at the same level as silicon. But the major one, which is still sort of the bottleneck or of these technologies, that the reliability and the lifetime. Although all the pressurized tests or all the accelerated tests have been very positive, but the outdoor testing data is still lacking. So that's the reason maybe the policymaker or some of the industries are still a little bit hesitant to go for this technology 100%. So just about the future of this technology, I recently published this as a perspective from my side, that what needs to be considered if you want to bring this perovskite to the real commercialization, to real market. So considering about the stability, performance, scalability, and another aspect is about sustainability. And because in many countries, including European countries and UK, we have a very sort of a strict regulation of utilization of some material like lead-based, for example, material that's been used in this technology. And this needs to be addressed carefully. Obviously, there are some argument against that, but yeah, what we discuss here is we need to discuss and understanding properly. But in terms of commercialization, these are my sort of future prediction of how this technology will come to the market. And I'll skip these one, but these are the scientific approach that we have done in my group and in collaboration with other leading groups in the field to address some of the big challenges. This one was about the challenge of the stability I mentioned earlier. So this is about intrinsic stability of the material because of the ionic nature. So there are some of the ions in this material can easily move under the bias, under the voltage, and under illumination. So we try to prevent that by a new approach, adding extra ions into the system and locking up them at the boundaries. The other aspect was to find out what is the reason behind the losses, behind the efficiency loss that we cannot reach the maximum sort of predicted energy efficiency we can get from this solar cell. And here it's a very complex sort of measurements and techniques we develop here to understand what are the performance limiting factors in nanoscale within our semiconductor that are limiting our performance. This was mostly about the defects, finding where the defects are and correlating it with the luminescence of the material. And we also discussed this about how to optimize the composition of the material to make it more robust, less sort of unstable, and make it better or more efficient. And this is always like a competition between various different composition to reach the final product. And another aspect which my group focused and published very recently in the past couple of months was utilizing this material for indoor photovoltaic. So when I call indoor, what I mean is utilizing not only the sunlight, but also the synthetic light. So let's say we are now sitting in a room and we are using some lamp or LED lamps or fluorescent lamp. And we can actually use our solar cell to capture this synthetic light, or we call it diffuse light from the sunlight as well, and produce electricity out of it. So it's abundant, another source of abundant energy that we have that we are not using its full potential. It's kind of I would say, energy recycling from what energy we are using from the lamp, from other sources to recycle it back into electricity. So this can happen using indoor energy harvesting. And one of the devices that can make this happen is indoor photovoltaic. So this is like a room that you might have been sitting now. So the intensity obviously is significantly lower compared to the outside light, which is about 1,000 or 100 milliwatt per square centimeter or 1,000 watt per square meter. And this is significantly lower intensity, but still we can make use of it and power a lot of devices that we are using just by using this light. There's a huge market for it as well, because I'm sure you have heard about Internet of Things and using a lot of sensors in our daily life. We are currently using, and this will be the growth of this Internet of Things is kind of exponential. So there will be millions or billions of sensors in the world that could be actually powered from solar indoor PV. I should call it indoor PV rather than solar PV. All right, so in terms of the material, obviously the perovskite is one of the best material to utilize indoor light compared to silicon or other organic or DSSC. It's been very efficient and very tunable. And this is the work we have recently published and been also very took a lot of attention from the UK media because here we discuss about saying goodbye to batteries by replacing it with indoor PV. It was a very funny title made by the journalist, but yeah. But if you have any question about this, we can discuss. But yeah, the meaning of here is not fully replacing the batteries, but replacing the need for changing the batteries. All right, so now about the scalability and commercialization of this perovskite technology, which is very promising. So there's a lot of companies around the world are focusing on this, and we have been working with some of them as well in the UK and abroad. This is one of the company I've been working with, and you can see this is the solar modules, 30 by 30, and this is the solar panel. So it's 1.2 meter versus 0.6 meter. So this is a huge panel made by perovskite. You can see it's very homogeneous, very nicely covered material, and it's a very high level. It's over 20% efficient in the module monolithic solar panel, and in this size it's over 24. So it's almost same level as silicon. So you can see it's coming to the market. And on the tandem side, where you can combine perovskite with silicon, is over 35%. I mean, this data is a little bit old. And I also recently visited one of the largest solar farm in the world, in China. It's called Great Solar Wall. So it's built in a Kubichi desert. So actually, sorry for the pronunciation. So it's 100 gigawatts solar farm by 2030, and at the moment it's about 5.5 gigawatts. So it's a huge solar farm. And the interesting part of this, and the reason I visited, was there is a portion of this solar farm is utilizing perovskite-based technology, which is quite promising. So you can see in this circle, so all of these PV panel are based on perovskite solar cell, single junction. So it's a huge news and huge progress in the field of perovskite. Within a decade is already coming to test, very serious tests in a solar farm. All right, so I think I have a few more minutes. I try to be very quick on the green fuel part. So this was the end of my talk about the solar energy utilization using photovoltaic technology. Now I very briefly want to talk about the green fuels, which I introduced earlier. So when we talk green fuels, it's mostly, maybe you already heard about green hydrogen or green ammonia or even green methanol. So this means that carbon neutral or carbon free alternative to the fossil fuels. So basically, when we say green hydrogen, so that means during the production of the hydrogen, we are using green sort of energy like solar or wind or other kind of renewables. And the whole process should be carbon neutral, so to be called green hydrogen or green ammonia or etc. And why we are looking for green fuels? So I talk about the limitation of the solar energy, about cost efficiency, etc. Another limitation for renewables in general is they are not a constant source of energy, right? So for example, we don't have sunlight all over the day, right? So we only have sunlight from a certain time in the day and until the sunset. So, and similarly with the wind, we don't have wind all sort of in the same intensity all around the year. In some places we have more, some places less. So you can see that it's very intermittent. So basically we need to rely on a very, if you want to use them, this kind of technology, we need to rely on a very stable and long-term storage system, which currently we don't have actually. So basically, normally most of these solar farm or winds are connected to the grids, which have another issue in terms of fluctuation, etc. But long-term storage is still a technology that needs to be developed in the form of green fuels. Because the battery technology, even the best ones, are still, we don't call them long-term, because you cannot, long-term, when I say it means at least 5 to 10 years or above 10 years of storing energy. So which cannot be achieved by batteries in the largest scale in a cost-efficient way. Another aspect is if we want to convince industries to decarbonize and contribute to the net zero goals, it's not easy just to tell them, okay, please use renewables and forget about your profit, right? So profit is the major driver of a lot of industries, or many, almost most of them, or majority of them. And if you just say, for the sake of environment, obviously you can say, you can imagine they will say no. But if you can bring some sort of profit for them, or we can offer them a solution that can be also profitable and also decarbonize their sort of CO2 emission, that would be a huge game changer, right? So this is what we want to achieve with this new electrochemical system to produce green fuel like methanol or ethylene. So this plot is very important because it's showing the price of these chemicals that we can produce from CO2 reduction or water splitting versus the energy content that they have. And anything above this line, this dashed line, is very sort of economically profitable for industry. So that's the reason we are focusing on making these chemicals out of CO2 reduction. So basically, what is important here is we are looking for direct electrocatalytic CO2 reduction to green fuels like methanols, because if we go indirect, that will increase energy system cost and reduce energy efficiency. So we are mostly want to focus on direct CO2 capture and conversion to fuels. And this is a very complex electrochemical reactions, as you can imagine. And we need to develop a catalyst that can sort of make this reaction happen, that are not super expensive and also based on abundant materials. And the other reason that we are focusing on green fuels, and specifically in my group, we are focusing, one of the major fuels that we are focusing in methanol or alcoholic fuels, is because they have a very high energy content. So energy content is measured based on the unit or based on the weight unit or based on the volume. So the ideal scenario is here, right? So you have the highest energy content per volume per weight. You can see that liquid fuels, alcoholic fuels are much better than batteries and much better than hydrogen gas in terms of both scenario. And this is just to give you a context. So basically, again, how large it will be in terms of the land we need to for production of the whole global energy needs in terms of storage. So if you compare the alcoholic versus compressed hydrogen versus lithium-ion batteries, you can see alcoholic fuels needs the least volume compared to liquid ion batteries or compressed hydrogen. And on the other hand, it needs the least weight compared to these two technologies. And the other aspect is the amount of infrastructure we need for alcoholic fuel is significantly lower compared to the other two. And there's already a huge market for this methanol. So if an industry agreed to use our technology, they can sell it easily because there's a huge market for it. And I skipped this part because of the time. And this is the project we started a while ago, and it's finished very recently, where we develop an electrochemical cell, which is the core of our system to convert the CO2 from biogas plants, from energy-intensive industry or petrochemistry, and make it methanol, and then use it in transportation fuel cell and create electricity back to the grid. And then also our electrochemical cell are powered by renewables, specifically by solar. This was a multinational project, and from UK we were the lead. And this is our technology. So again, because of the time, I don't go into the details, but this is basically the core electrochemical cell. We have anode and cathode that are separated by an ion selective membrane that can sort of, and normally the CO2 absorb in the cathodic part and create the methanol in this region, and we create oxygen in the anodic part. This is the prototype we developed during this project that can actually produce methanol, green methanol. And another aspect which might be of interest to some of you is about the socioeconomic impact or regulatory measurements, social impact and economic impacts that we calculated during this project. And we show that the global warming potential is significantly reduced if we choose the next CCUS prototype, our project prototype. And another aspect we also consider is safe by design. So we need to make sure whatever material we develop are safe, or they have a promising supply chain to be used in industry. And so we look at this from the raw material to operation to long-term health and ecological impact. And finally, this is the new project we started this month in 1st of November, where we are going to ultimate solution, which is the integration of photovoltaic cell with the electrochemical cell in one monolithic system, where we can produce green methanol by combining this PV technology based on perovskite and the electrochemical cell. It's a very new design. And here we can utilize a good portion of the solar spectrum by our tandem design, and also power our electrochemical cell for CO2 reduction, direct CO2 reduction to methanol with over 12% solar to methanol efficiency, which is quite significant. And finally, so the key challenges and opportunities for the solar energy future. So key challenges is about the scalability and manufacturing bottlenecks, especially for this complex system of solar cell with electrochemical cell, about material sustainability, end of life, recycling, operational stability of the system, how we can integrate them within the grid without a huge loss of energy, about how we can make this technology economically competitive with the alternative like conventional sources. The other aspect is metrology and standardization of this system in terms of measurements and how we can reliably measure them and assess their efficiency. The opportunity is huge. So basically, on the indoor PV side, we discuss on BIPV side, on flexible perovskite, and also on solar fuels, on the solar fuel side, which there are a lot of opportunity for startups in these fields. There are a lot of them, a good number of them are already active, but there are rooms for new ones as well with new innovations. And my last slide about conclusion and key take-home messages. So we have an urgent need for new energy materials and devices to address the climate sort of challenge. And solar energy will be definitely dominate our future electricity system. It's just a matter of time. Solar fuels are essential for our deep decarbonization and if you want to reach net zero. Major challenges, as we discussed, stability, scalability, and integration. Halide perovskites is one of the key or good solution, and he has a huge potential. And yes, the PVEC integration, we can rely on this system for supporting the global net zero goal by 2050. All right, so at the end, I would like to thank my group. This is my research group. A lot of, and specifically Siming, who work on this indoor PV one, and all the funding bodies like Horizon Europe, Next CCUS project, Accelerating CCS Technologies, Department for Net Energy Security and Net Zero, Henry Royce Institute, and all other funding opportunities and all the collaborators. And before finishing, so I have a PhD position in my group starting from next year, and the position is open now until early Jan for application. So if you are interested, please do get in touch with me. And this is a QR code you can scan and will directly bring you to the project. But the project will be on turning CO2 into clean fuels with advanced materials. So basically, it's about the solar-driven perovskite tandem cell for methanol production, which we discussed a bit earlier about. It's a huge and very interesting project. If this would be of interest, please do get in touch. And thanks very much for your attention. I hope this was useful for all of you, and very happy to take any questions now.
Thank you so much for your informative talk. There are some questions that people typed up in the sign-up form. So someone has asked about how solar and clean energy advances will be used in like a smaller scale, so like in microgrids or in areas where I guess it kind of touches on what you've said about areas where energy is quite scarce or in electricity.
All right, very good. Good question. So yes, so one of the benefits of the solar energy compared to other renewables is you can actually use them we call it off-grid, right? So you can utilize it or decentralize your energy production in different countries, especially in the rural area or the areas that grid cannot reach. There are still some places in the world like that grid connection is not possible or is not economically viable. So solar energy can make the difference. So basically, it can be installed almost on any places that have sort of some surface area available for the solar panels to be installed. And the key challenges there is about the storage or energy storage technology, right? So let's say we produce a lot of energy using solar, but if we cannot store it efficiently, there will be a lot of losses, right? So So the challenge there is about energy storage. So obviously the battery technology has improved quite significantly, especially in the car industry, which is very promising. But if you want to think about in the future to have very decentralized energy production, we need to think about long-term energy storage solution, such as green hydrogen, such as green ammonia or green alcoholic fuels. Green alcoholic fuels like methanol we discussed is more, from my perspective at least, is more promising because it has less safety issue and also it's already very compatible with our current infrastructure that we have for the oil and for the oil sort of petrol, etc. So this could be a good game changer if we can make this system efficient enough that it's economically also comparable with other renewables. So that this would be a huge game changer.
Thank you for your answer. Next question. Someone asked, as you mentioned, perovskite is easy to fabricate using the printing process, but could you explain further why it is still difficult to scale up? Are there any other nanofabrication techniques we can use to produce perovskite?
Yeah, that's a very good question. So yeah, so in terms of scalability, there have been huge progress. So nowadays, I won't say it's very hard. It's relatively easy to make a perovskite larger scale. You saw the panel I showed you earlier. So let me bring that slide again. I don't know if I'm not sharing yet. So let me share again. It might be useful to show the slide as well. Right. So these are the panels, for example, one example. So these are all prepared using printing techniques. The major challenge, though, is how we are making this material without one aspect is to make them homogeneous throughout this large scale, large size, which has been to some extent already been resolved. The other aspect is how we can make them quick enough that could be compatible with the current PV manufacturing system, which is mostly based on silicon, that can be implemented in their system without a huge change in their infrastructure. So this would be a relatively big challenge at the moment. So because some of the printing technique that developed for perovskite, because it also involves some annealing step, although it's quick, but it's still not fast enough to cope with the current infrastructure. So that's one of the challenge. But the major challenge again is how we make this material to larger scale in a homogeneous way, same quality of the material all over the sample. You can see it's a 1 square meter, right? So it's quite a large surface. In a normal printing, you don't care that much about the homogeneity or nanoscale homogeneity, but in a solar cell technology, it's very important because the traps or the reason that we are losing efficiency are those nanoscale traps that created during the fabrication process. So that's the reason we need to be very careful when we make this material at a larger scale. And still, I mean, the progress have been great because the record efficiency is now 27%, and the module efficiency is about 24%, and the panel efficiency is 21 or 20%. So it's not too far away. So it's to some extent it's already been sort of addressed. You can imagine that even for silicon technology, which is a very mature one, the record efficiency, the smallest scale is 27%. The module efficiency is about 24 to 23%. So you can see you will always lose some sort of efficiency when you go to a larger scale. That's quite normal because of the some connection issues, some the homogeneity issue, etc. So this is quite normal, and I think perovskite had a lot of good progress in the past 5 years to reach this very advanced stage. So I think the second part was about any nanofabrication techniques. So just to comment on that, so the current techniques people are using are mostly solution processing, such as slot die coating or inkjet printing, if you have heard about them. So which are been very useful and could be the game changer for the manufacturing. But there are other methods you can use, like for example, you can use thermal evaporation, like PVD, physical vapor deposition techniques as well, that give you a better control. But on the other hand, you need to consider the cost, right? So it's always a compromise between the cost of that manufacturing technique at larger scale versus the quality. And yeah, so basically, at the moment, from my perspective, inkjet printing and a slot die coating are the major two technique that could sort of potentially contribute a lot towards initial commercialization of perovskite solar cell.
Thank you. And then the second question is, do you see geopolitics playing a larger role than technical innovation in determining which solar technologies scale commercially?
Very good question. I would say yes, because it depends on when you say larger role, you mean yes. So yeah, you're comparing this to technical innovation. So obviously, if you can make an energy solution that is cheaper and it's easy to produce, so I mean, everyone will use that, right? So we'll go above it without any problem. But in terms of geopolitics, it's playing a role. I would say yes. I mean, one of the difficulty we have at the moment with the PV technology is it's it's actually dominated by almost very handful of the countries, right? So mostly, I would say most of the PV technology are produced now in China and maybe very little in the US and almost nowhere else in the whole world. So this might be a problem in the future, specifically if you think of a widespread adoption, right? Because then it's like a monopoly that's this technology has been only produced by one country, and there will be a lot of resistance politically from other countries to deploy the solar technology, even if it's cheaper than, let's say, conventional sources. So to prevent that, I mean, the new technology like perovskite is a good way because it does not require that advanced manufacturing sort of infrastructure that you would need for silicon. And it does not rely significantly on the manpower if it become because again, it's like a printing method, right? So how you print newspaper, you can print your PV devices, and it could be fully automated, so you don't rely on manpower anymore. So from my perspective, so if this technology become the reliable technology and tick all the boxes in terms of outdoor performance, then it could change the game, and will be less resistant to other countries to deploy solar technology rather than just rely on silicon. So yes, I mean it depends. It's very dependent on the at the moment it's a little bit geopolitical because of the way that it's produced, but it could be actually change in the future. This new technology come to the game. And I think many countries these days are trying to decentralize their energy production, and specifically because obviously it's very much sort of in favor of the country if they can produce electricity locally rather than centrally, in terms of the security of the country in the case of unfortunate event like wars, and also in terms of a better service to its customers. So yes, thanks for the question. It was Aline, right? So thanks. Nice question.
Okay. Thank you so much for giving talk today. Thank you for everyone who's joined us. We hope you found it insightful. And Energy Society will be having more events soon. Follow us on Instagram to find out more. Thank you again, Professor.